countdown, we'll go to the slide and go from the current slide. Okay. Now, by way of announcement, and it really won't affect this class much, is it Monica? Okay. 6 out of 7, we're almost there. Okay. But on Tuesday, we will have class as normal, but as soon as that 9:50 arrives, I've got to book it to Birmingham because I have a doctor's appointment. I think I told you all about that first day, but maybe not everybody was here. I have a mild form of leukemia, and my hematologist only sees patients on Tuesday morning. So hopefully this will be the only time this term that I'll miss classes. But this one is fine. It's my next class wiped out. So some of you are in that. Yeah, you are. Okay, and Pratisha is. So I won't be here for the second class, but I will be here for the first. Okay. Now, any questions on anything we've done up till now? Okay. We were on example 6, page 7, section 1.1. Functions. This title is weird. Function versus solution. Okay. Don't know what it means here. Okay. We were talking about in example 6a, talking about the function y is equal to 1 over x. That's a function. But when you have y, let me get my pen set up. Y is equal to 1 over x as a solution for a linear first-order differential equation. For instance, this one, x y prime plus y equals 0. Now, again, the way this book presents things, it goes over all this stuff, but never tells you how to get a solution, but just, getting you used to thinking. I don't know what the purpose is. The differential equations text that I had when I was in college was so good I could almost read the text and understand it without anyone talking at me, because I had a really lousy professor for that course. That was one of the few that was really a rotten professor. But I just read the book, did the problems, and wound up better off than the other students because he was terrible. Okay? So it hasn't told you how to do this, but we can check and see if indeed that is a solution to this. How would we do that? What would be your first step? Take a derivative. Y prime is equal to? Second? I can't hear you. Log of x? Okay, if you're doing an integral, that would be true. A derivative, it goes the other way. Here's what I suggest. On the y is equal to 1 over x, write it as x to the minus 1, right? Now take a derivative of that. What would that be? Negative x to the minus 2, which would then be, writing it back in fractional form, that would be negative 1 over x squared. Okay? Got it? All right. So let's plug that in here. X times a negative 1 over x squared, that's your y prime, plus y, which is 1 over x, right? Is that equal to 0? That's the question. Well, x will go into x squared, x times, so this will be minus 1 over x plus 1 over x, sure enough, is equal to 0. So, absolutely true, that y is equal to 1 over x is a solution for this ordinary differential equation. Or is it? Okay? It depends on where you are. Now remember the function, this is what we did last time, 1 over x is defined for all real numbers except x equals 0. Not defined there. Well, this is a solution for this thing, but remember when you do solutions for differential equations, you have to specify intervals. So this is true this is a solution here. Y is equal to 1 over x, only if you are minus infinity to 0, not counting 0, or 0 to infinity, not counting 0. In any interval within that, and we talked about this before, -3 to -1, that would be okay. 7 to 45, that would be okay. But -1 to 7 would not be okay, because that would cost 0. So you have to specify an interval, and on this one, you can't say, just leave it there and say all real numbers, or assume all real numbers. It's not. It has to be some interval that's strictly on the negative or strictly positive. Cannot include 0 on the interval. Okay. So when we say that y is equal to 1 over x is a solution of that differential equation, we have to specify the interval over which it's true. For instance, you tell me, -3 to -1. Would that be a solution there? Yeah, good. How about 1/2 to 10? Yeah, sure. Okay. How about negative infinity to 0? Yes. 0 to positive infinity? Yes. Okay. But, well, they don't give any. Okay. I thought they would give some that wouldn't. Okay. So, anyway, we had already said most of that. Now, here's another bit of nomenclature. That's a lot of what this first chapter is dealing with, is just getting used to the language of differential equations. We can have what they call explicit solutions or implicit solutions. Now that may sound sort of familiar to you when you were doing derivatives. You can take a derivative explicitly like we did up here, okay? Or if you had a really complicated looking thing, take the derivative using chain rule and things like that, and then solve for the derivative. That would be an implicit differentiation, okay? Well, let's see if that has any bearing here. You should be familiar with those terms, and I just mentioned them. A solution in which a dependent variable is expressed solely in terms of the independent variable and the constants is said to be an explicit solution, okay? And let's just show a few of these that we've already had. Let me go and clear the screen. Not everybody have books, so I have to write more of this down than I would think. This is on page 8 now. Top of the top paragraph on the on page 8. Okay. Earlier we had a differential equation that the solution was y is equal to 1 over 16 x to the 4th. Explicit solution. Okay? We had another one that y is equal to x e to the x. Explicit solution. The solution is given as a function of the independent variable and constants. That's all. Okay? Explicit solutions. The one we just did, y is equal to 1 over x. Explicit solution. Okay? Now, and these are, and by the way, now they give them, I wasn't looking ahead too much, dy dx is equal to x y to the 1/2. That was a differential equation. That's the solution to. This is the one that was y double prime minus 2y prime, lost it, plus y is equal to 0. That was the one. That's the solution to, and we just did this one, and that's the solution to x y prime minus y, plus y is equal to 0. So that's the solution for that. So these are all explicit solutions to those differential equations. Okay. Now, you have sometimes the trivial solution, y is equal to 0. That would work in the first one, and in the second one, it wouldn't work in the third, okay, because y is never 0 in that thing. If you think about how that looks, it's down here and up here, but y is never 0, okay? So that would be an explicit solution. They say of all three equations. Yeah, okay, I'm sorry. I wasn't thinking, I was looking at the solution, but not this. If you put y equals 0, y prime of 0 would be 0, and 0 plus 0 is 0. So sure enough, that would be an explicit, a trivial solution would solve that one as well. Has nothing to do with the rest of the solutions, but it does solve that one. And the other two, it fits right in with the others. Okay. All right. When we get down to the business of actually solving some ordinary differential equations, you'll see that the methods of solutions do not always lead to explicit solutions. Okay, y is equal to some function of x. This is particularly true when we attempt to solve nonlinear first-order differential equations, and often then we have an expression that looks like this: g of x and y is equal to 0. Okay? That defines a solution implicitly. So here's a definition for an implicit. Blah, 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 talking about it. Now here's the blah, blah, blah definition. A relation, I'm writing this only because not all of you have books yet. A relation g of xy, just like I had before, equals to 0, is said to be an implicit solution. I'm skipping some words here. Implicit solution, abbreviating like crazy, of an ordinary differential equation. And again, ODE, ordinary differential equation, so I don't have to write all that out. And that would be equation 4. If you turn back, that was the equation, several pages here, the f of x, y, y prime, y double prime, y triple prime, up to y to the nth derivative of y equal to 0. That standard kind of equation there. On some interval I, okay, provided, this is a requirement here, provided there exists at least one function, okay, function Fn, phi, okay, that satisfies the relation as well as the differential equation on I. That's really nebulous, okay, that satisfies the relation as well as the differential equation. On that same interval I. Boy, what a vague sounding definition that is. And then here's why it's vague. The next sentence. It is beyond the scope of this course to investigate the conditions under which that relation defines a differentiable function in x, okay, phi. We will assume that if the formal implementation of the method solution leads to that answer, then there exists at least one function that satisfies that. So blah, blah, blah. Let's do example 7. Maybe that'll make things a little clearer. Hopefully it will. Here's a relation. Pretty common one too. You've seen it. X squared plus y squared is equal to 25. Now, you tell me what that is. X squared plus y squared is equal to 25. That's a circle of radius 5. 5, okay? Circle of radius 5. Okay, we know what that is. Now here's the key, folks. That's not a function, is it? A circle of radius 5 is not a function. Y is a function of x, because if you think about a circle, vertical line test fails in many places, okay? So that's not a function. It's a relation, and that's what they said at the beginning. But indeed, they say it's an implicit solution of this differential equation. dy dx is equal to minus x over y. Okay? Now, sorry, for some reason my nose has started running. Let's see if indeed that's true. Okay? And again, to do dy dx with that equation, you have to differentiate it. Well, you don't have to, but the easiest way to do it is an implicit differentiation. How would you take the derivative of that equation right there with respect to x? Let me write it out for you. D of x squared dx plus d by dx. I had an Indian student I was tutoring one time, and he always said, d by dx. I didn't know what he was saying for the first 15 minutes. I kept saying, what is he saying? D by dx, okay? But that's d by dx of y squared is equal to the derivative, d by dx of 25, okay? So what is d by dx of x squared? 2x, okay? Plus d by dx of 2y, of y squared. I'm giving you the answer. What is it? 2y, but there's a second part, isn't there? Chain rule. See, x is not a function of x. dx dx is 1. But here we have to have a dy dx, okay? Okay? And what is d by dx of 25? 0. Got it. Okay? Now we solve for dy dx. Okay? So let's subtract 2x from both sides. And that will give us 2y dy dx is equal to minus 2x. And then what would we do to solve for dy dx? You tell me. Pretty simple. Divide by 2y. Okay? The 2y's go out here, and you're left with dy dx. And over here, the 2's go out. They've been dating. No, I'm just kidding. Okay, and what do you have? Minus x over y. And that's exactly what that differential equation. Now, again, the book is showing you, okay, here's a solution. It's a solution for that differential equation. Verify it. They haven't yet told you how to find these solutions, which kind of gripes me because that seems to be what we're here for. But anyway, they did it just like this. But that's an implicit solution of the differential equation on the open interval from -5 to 5. Okay? It's not a solution outside of those. For me, can't figure out why they didn't include 5 in it. I would put the closed interval -5 to 5, but maybe there's a reason they didn't want that. Oh yeah, I think you know the reason. Yeah. If you think about a circle, its derivative here is under 5. Right? Vertical line. Tangent vertical line. So that's why they said open interval -5 to 5. On, because you always have to give the interval, on I equal -5 to 5. Open. Okay, you can't include that because the derivative is not defined at the endpoints there. Now, there is another way you could have done the problem. Okay? That's if you had split this one out. At first I said the only way you could do it was implicit. I said, no, there is another way. Here's the other way. You could have solved for y. So y squared, subtract x squared from both sides. Y squared is equal to 25 minus x squared, and then take a square root. Y is equal to, but when you take a square root of both sides, what do you have to include? Plus and minus. It would be plus and minus the square root of 25 minus x squared. In other words, you have two solutions. The square root of 25 minus x squared and minus the square root of 25 minus x squared. And as I said in the beginning, this is not a function. So it's not really too surprising that it's, when you break this down, you get two things. So you can take the derivative of this one, or you can take the derivative of that one, and it'll give you two possibilities. And again, that's a little messier. So much easier to take the implicit differentiation, but you will get the same results. Okay? And both of these, by the way, are functions of x alone. So you can do it implicitly, explicitly. If you can do it, that would give you two phis of x's that would work. Okay? So that may make the definition make a little more sense. Okay? And again, a lot of blah, blah, blah. Now, you don't have your books, and let me, okay, go to this page. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now, this isn't quite going to look like a circle, number one, because I'm drawing it. But number two, or at least in my mind, well, maybe so. On my screen, it stretches this a little bit, and those aren't squares. On this one, it projects as squares, so maybe it'll show up closer. But you see, if you drew the circle here, if I could draw a circle, which I can't, okay, pretend that's a circle, okay? Now, that's a relation that satisfies this, but the function that does would be, give me another color. Red, okay? This would be the positive square root, and give me another color. Green, okay, that would be the negative square root. So you see, you could do it as a relation implicitly or two different functions explicitly, okay? And you could go about either way. Now, that being said, there we had two possible solutions. Did someone say something? Oh, okay. I thought I heard something. A lot of times with differential equations, now, okay, back off a minute. When you're undoing a derivative, what are you basically doing? See, a differential equation involves a derivative, right? When you're undoing a derivative, what are you doing? What's the calculus operation that undoes derivatives? Integrals, okay? And when you were doing, especially indefinite integrals, what did you always have to put at the end? Plus c. Or somewhere in that problem you had a c. Because there's more than one possible function that has that as a derivative, okay? If you have, let's say, that function, okay, and that derivative, well, that function up there has the same derivative. That's the plus c to it. So really what you wind up with is a family of solutions. So quite often in differential equations, your result will be a family of solutions. Now, what did we need to know if we wanted a singular solution? Second? A little less. Okay, you could, the starter endpoint, basically you need to know some value. And sometimes it's only one that's required. Because if you know one point on it, then you know rather than this function or this function or this function or this function, if you know this point's on it, it's got to be that. Okay? So you need a value. It could be an initial value, it could be a boundary value like you were saying, an endpoint. It could be any particular point. Well, okay. Higher level differential equations, second, third, fourth order, okay? Then you're going to need 2, 3, or 4 points because for every derivative you're going to need another value, okay? I want to say initial value, and that actually is what we usually use. So, a family of solutions, and again, they're going to explain all this much better in Chapter 2, but they're kind of getting you ready for it, for example 2. So let me, again, this is a good book and a good author, and lots of people like it, but it seems like it could be organized a lot better than what she does, or he does here. I think it's he, yeah. Okay. All right. The reason I said she, the person who recommended the book to me was a she. Oh, yeah, this is a great book. Okay. And it is good. It's okay. The first 2 or 3 books I tried to teach from were awful. This one's much better, but still I don't like its organization. Okay. We'll get to this in Chapter 2, but here's what we got. Remember let's go back to black here. Remember our definition of the generic differential equation, capital F of, well, this is first order, x, y, and y prime equals 0. Okay? That's your equation 4, but only for first order. Okay? We usually obtain a solution by containing a single constant or parameter c. Okay? Because you only got one derivative in that. So you're going to have basically one integration, so you're going to have one parameter c. Okay? So we call that solution with that c in there a single parameter solution. Okay? One parameter family of solutions. Okay? But if you had, and this is what I was saying just a minute ago, f of x, y, y prime, y double prime, dot, 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 up to and including y, the nth derivative of y equals 0. This is going to yield an n-parameter system because you got to have a parameter, a constant, for that derivative, for this, for every one of those n derivatives. So that would give you an n-parameter family of solutions, which can be sort of mind-boggling trying to figure out what it is. Okay? Now, for that f, and I sort of skipped this and I shouldn't have, that solution, the set of solutions, could be expressed, I would have said a little f, but they're using capital G. This will be its solution, and it'll be a function of x, y, and then some constant c. That's what makes it a single value. For this one, if you got the solution, you've gotten rid of all the derivatives. But in place of each derivative, you got another constant. So its solution could be something like g is a function of x, y, c1, c2, c3, dot, 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 up to c sub n. Okay? So it will have, the solution is in terms of x and y. You got those in there, especially if it's implicit. If it's explicit, you may not even have the y in there. But then you'll have enough constants to cover each of your derivatives. Okay? That's one way to express it. Okay? Now, this means that a single differential equation can possess an infinite number of solutions, okay? C's could be anything, okay? Even a single C could be anything, okay? Corresponding to an unlimited number of choices for the parameter or parameters, okay? The solution of a differential equation that is free of parameters is called a particular solution. So that's a new term here, a particular solution. Now, let me back off. Remember that equation that gave you 1 over x as a solution, okay? But had a 0, would also, the trivial solution would also be a solution to it. Didn't fit here, it didn't fit here. It was there. That would be a particular solution. It had no parameters dealing with it. You know, there was no C multiplied or added or anything else. 0, 0 would just be, it wouldn't have a C in it, okay? So that's one really bizarre, simple case of a particular solution. But you could have others that this function with no parameters is also a solution that's called a particular solution. This will make more sense when we do the problems that contain those. The parameters in a family of solutions like this, okay, are arbitrary up to a point. The parameters, okay, those are the C's, okay. For example, it says as in 9. Where is equation 9? Nope. I don't see 9, okay? We haven't gotten to 9 yet. I don't know what they mean by that, okay? But it looks a lot like the solution for example 7. Maybe they meant that to be a 7. What if your solution, remember in example 7, was x squared plus y squared is equal to c, okay? Not 25, okay? Well, that meant any circle is going to fit this, the differential equation. The circle we were dealing with had 25 for C, okay? Okay. However, it's understood that the relation should always make sense in the real number system. Because what if you said C is equal to negative 25? Would that make sense? X squared plus y squared equals negative 25. That's always positive. That's always positive. The sum's always positive. Can't be a negative 25. Can't be a negative 1 or negative 0.3 or any negative number. C has to be positive. So you can't just throw any C out there. Any positive C will work. It's completely arbitrary, but negative C's, nope, not allowed. So you can't say C is completely arbitrary in a problem like that because you can't put a negative number in there. All right. Now, another kind of nebulous example here. Here is a solution they're telling us. Y is equal to Cx minus x sine x. No, I'm sorry, minus x cosine x. Yeah. Again, they just pull this out of the air, or some body part we won't mention, okay? Minus x cosine x. They say, for all real values C, the one parameter family, this family here, Cx minus x cosine x, is an explicit solution of this differential, a linear first order equation, differential equation. Here's the equation. X, y prime, minus y is equal to x squared sine x. Now, again, they haven't told you how they got that solution, but just that it is. Being the cynic that I am, I want to make sure they said it right. So what's something we can do to verify that? Say again? Anybody? Take a derivative, okay? Now, I say this in my Cal 1 class, but it's not a bad thing to do here either. And if I hope this isn't offensive to anybody, but I don't know if you attend church or not, but quite often in a lot of the churches, they'll have children's sermon, right? They'll have the kids come up and then they dismiss them so they don't have to sit through the sermon. No, I didn't say that. But anyway, when they get them up, usually somebody's up there leading them, the pastor or some youth leader or something like that, and they'll usually lead off with a question. And quite often kids are there. Okay? They don't know why that. Finally, one kid will usually say, Jesus! Okay. Now, why is that? Usually a safe answer in most churches. If you ask a question, you don't have a clue what they're asking about, say Jesus. No one's going to say that's the wrong answer, right? So in this course, and especially in Cal 1, when I ask you a question, you have, give a kid, take a derivative. Okay, that's going to be your standard answer. Okay, not always, but it will most of the time. That's your Jesus answer. Okay, so let's take a derivative of this. And what do you get? C, that's yes in Spanish, okay. Help me. Say again. Minus, say again. Okay, not quite. X sine x, is that what you said? No. Wait, cosine x, is that what you, okay, yeah. Okay, cosine x, okay, now what's he doing there? When you take the derivative of that part, product rule. Product rule is derivative of the first times the second. That's what he did there. What's the second part? Say that again. Huh? Plus x sine x. I'm hard of hearing, okay? So it's not that you're speaking too softly. I can't hear, okay? Plus x sine x, okay? That's the second part of it. Is normally it would be a plus because your signs can really throw you off. If you take a derivative of that, that would be cosine x, and then it would be plus x times derivative of that, which would be a minus sine x. So minus x sine x, but you have a minus in front, which makes that one minus and that one plus. Okay. Make sure you got it. Okay? So there's your y prime. So now let's plug in that to this equation. X times c minus cosine x plus x sine x minus y. Well, what is y? Cx minus x cosine x. Okay? The question here, is that equal to x squared sine x? All right? Well, if you clear parentheses here, you have a xc, or let me write it as cx. That just sounds better. Okay? C's will be a coefficient. Minus x cosine x, right? You tell me the next part. Plus x squared sine x. You tell me the next part. Minus cx. Watch those signs. Huh? Plus, say again, x cosine x. Is that equal to x squared sine x? Well, let's see. Here we have a cx. There you have a minus cx. That adds to 0. Here you have a minus x cosine x, a plus x cosine x. That adds to 0. And sure enough, that's true. Okay, you remove the question mark. That is true. So sure enough, that one parameter explicit solution is a solution for that differential equation, this one right here. Okay? Now, and where is it true? All real numbers. Because this solution, x's are good everywhere, cx's are good everywhere, x cosine x is good everywhere. There's no limitations at all, either in the solution or in the original equation. That is a one-parameter solution everywhere on the interval minus infinity to infinity. Okay? Now, I wish you had your books. Okay, for those who do, you can look at the figure here. Okay? The book what? It's on Google? Okay, great. If y'all don't know how to get it, find out from her, okay? Monica will tell you. Okay, here is a graph, multicolor graph, of a few of these solutions for different values of C. Okay? The purple one is down here. That's when C is very, very large, I guess. Okay, because they don't even give a value for it. The red one here is for C, say C greater than 0. I guess anything above that. The blue one is the C's equal to 0, and the yellow and greens down here are for C's less than 0. So they're greater over here, lesser down here. And I don't know if you remember these from trig class. These are called damped, with a P in it, periodic functions. With a, you got a CX added to it. Okay. So that's your family of solutions. If you knew any point on the coordinate system, not any point that made sense, you could figure out what it is. You couldn't have 0, 7. That's never going to cross the curve, because 0, 0 is the only value that it crosses x equals 0. But any other point out here, right down here, if you had a point here, continue doing your curves until you get one that goes through that point, and then you figure out what value of C that is. Okay? So all you need is a single point if you have a one-parameter system. All right, let's go to the B example here. Okay? Here's a two-parameter family, and again, they just pull it out of the air or somewhere, and y is equal to C1 e to the x plus C2 x e to the x. Okay? They say that's an explicit solution, meaning you don't have any y's on the right-hand side. The only y is isolated on the left. Explicit solution of this linear second-order differential equation. Y double prime minus 2y prime plus y is equal to 0. Okay? Now, we had that differential equation before, but we only said this is a solution for it. We didn't say it's the only solution. This is your two-parameter explicit solution. Every solution is going to be found in there, unless there might be a particular solution that didn't require any parameters, which we aren't going to mess with now. What are we going to do first? Verify. Okay, take it. Okay, very good. He remembered. Okay, y prime is equal to what? C1 e to the x plus C2, okay, and then you had e to the x, right? Help him. Plus C2 gone. Yeah, almost had it. X e to the x. Very good. Okay, Now, you could have just factored the C2 out and just taken the derivative of that. Derivative of this would be, derivative of the first is 1 times the second, plus the first, x, times the derivative of the second, e to the x. Yes, and the C2 is multiplied by both. So, yeah, product rule works. Okay? But we also have to do, take another derivative, okay? Second derivative. And that would be, oh, and by the way, let's clean this up a little bit. That would be, do I want to? I think I do. Do I or not? It doesn't really matter. Let's go on and take a second derivative of it. What do you get? Derivative of the first is C1 e to the x plus C2 e to the x plus C2 e to the x plus C2 x e to the x. Now this one I am going to simplify a little bit. C1 e to the x plus 2C2 e to the x plus C2 x e to the x. Okay. Just because those two terms are exactly the same. Started to do this up here with the coefficient of C1 plus C2. I said that may get a little confusing. Let's just go with it. So now let's plug it in. As you might guess, this is going to take a while, okay? Because your y double prime has 3 terms in it. There'll be C1 e to the x plus 2C2 e to the x plus C2 x e to the x minus 2 times y prime. Y prime has 3 terms. And that'll be C1 e to the x plus C2 e to the x plus C2 x e to the x. Okay? Plus y. Well, the y has 2 terms. C1 e to the x plus C2 x e to the x. The question is, I didn't write down my, oh, there it is. Is that equal to 0? All this thing, is that equal to 0? Let's see. This is a lot of work, writing, but you probably can look at it and tell. Here's a C1 e to the x, a C1 e to the x, and here we have a minus 2 C1 e to the x. Those add to 0. I'm being really lazy here. Hopefully you don't mind. Here's a 2 C2 e to the x, and here we have a minus 2 C2 e to the x. Those add to 0. Okay? And here we have a C2 e to the x e to the x, and here we have a minus C2 x e to the x. No. C2 x e to the x, and another one that's 2 C2 x e to the x minus 2 C2 x e to the x. Sure enough, those all add to 0. Okay? Now, I should have actually written out that middle term with the minus 2 times all of that, but I was just too lazy to do it. Okay? You got it? Was that okay? All right. Good deal. Now, okay. That's an explicit solution. Okay? If you take a look at the figure on this one, oh man, okay? You have 2 different C's that you can plug in, and they just show some of the solutions, okay? It's hard to see here, the grid, okay? The red, green, and blue, here's the red, there's the green, and there's the blue, okay? Or when you have C1 of 0, C2 of 5, that's the red. The green is C1 is 3 and C2 is 0. That's that one. And when you have the blue one here is C1 is 5 and C2 is 2. Okay. So you see you can have some incredibly different looking graphs depending on what value C's you have. And you have an infinite number of both C1s and C2s, so it really can lead to a lot. That's why you need to know some points. Initial points. Right. A lot of problems you're going to leave is nebulous answers like that. They could be an infinite number of graphs. Okay? Now here's the key though. When x is small enough, everything's heading towards 0. Because e to the x is going to 0, and if x, whether it's positive or negative, x is going to 0. No, if x is getting very large negatively, that's what I meant to say. Large negatively, e to the x is going to 0, and x e to the x, if x is large negative, even though it's a large number, e to the x dampens it real quickly, so that's going to 0. Okay? And it's hard to tell on here, but you'll see that just about every one of these. Now, if C2 is 0, then that's going to 0 from the positive side. If C1 is 0, that's going to 0 from the minus side. That's actually very large negatively. And if it's something in between, it may stay positive for a little while and then go negative. So you get all sorts of answers. But in the long run, for very large negative x's, they're all zeros, or going towards 0. Yes, limit to 0. But anything on the right is a mixed bag, just going all over the place depending on your seats. Okay, now, sometimes a differential equation possesses a solution that is not a member of a family of solutions of the equation. That is, a solution that cannot be obtained from your parametric equation. Not possible, okay? Such an extra solution, now before we had a particular solution for a given value, now we have something called a singular solution, okay? These aren't extraordinarily clear, but hopefully it'll make some sense. For example, we've already shown, we've given this example like 2 or 3 times before, okay, they have, that y is equal to 1/16 x to the 4th, okay, and y is equal to 0 are both solutions for this differential equation. Dy dx is equal to xy to the 1/2. Okay? Now, right now, and this is why I paused, I don't, and these are both solutions on minus infinity to infinity. X has any value in the world. And what I can't figure out is why they're using this as an example. Because if you put, well, I guess that's why. When x is equal to 0, certainly y is equal to 0. But they're saying y is equal to 0 no matter what the value x is. That's also a solution. So basically, whereas this shows a, remember, coordinate function, something like that, okay? That is also a solution for any values of x. So yeah, I guess that's why they're using it. Okay, the extra solution there is a singular solution. Okay, it has nothing to do with the others. Okay, now when we get to Chapter 2, Section 2.2, we'll actually solve that differential equation, this differential equation. You'll see that it comes up with a parametric form of equation, which is this. Y is equal to 1/4 x squared plus c squared. Okay? That will be our, and this will be true only for c's greater than or equal to 0. Okay? Okay. Can't tell you right now why that's true, but it will be. Okay? Now you'll see that solution is true when c is equal to 0. That's what you get. But you could have other c's in here not equal to 0, and there are also going to be solutions to this. Now, if I felt really frisky, I think I would say take a derivative of this. It's not going to be too bad. In fact, it would be pretty reasonable. Well, it still would be bad. Okay. But it would, you'll see that works. I guess we need to do that, don't we? Just for the practice. Yeah. Sorry about this. The book didn't do it, they just threw it out there. Okay? So let's do it. Now, if we're going to take a derivative, let's use the chain rules to keep us from having to have all the cross terms. What would be the derivative of that? Second, 2 times 1/4 x squared plus c to the first power times 1/2 x. Okay? The 2's will go out, and what you have then is 1/4 x cubed plus cx. Right? Do it right? Okay. Now, let's plug that in here. There's your dy dx. I should have written it that way. And let's write 1/4 x cubed plus cx. Is that equal to x times the square root of y? Okay? Right? And the y is given as a perfect square, so its square root is going to be 1/4 x squared plus c, right? Okay? Now this will be 1/4 x cubed plus cx. Yep, indeed, those are exactly the same. So that is your one parameter, because you only had a first derivative there, one parameter family of equations for any value c. The one we did before happened to be with c equals 0. But you have an infinite number of them. Okay? But y is equal to 0 doesn't fit here. Okay? Certainly it is when x is equal to 0 and c is equal to 0, but that's the only special, very, very special case it is. Y is equal to 0 also is that y is equal to 0, dy dx is equal to 0, and x times the square root of 0 is 0. Yeah, that's a singular solution, okay, of that system of equation. You don't get it from your parametric equation. Okay. Now, let's go to a new kind of thing. And really, I think they need a space between those two paragraphs to let you know this is a new, almost a new topic. But in all the preceding examples that we've done, we used x as the independent variable, y as the dependent variable. But remember, we can have an ordinary differential equation if you had a single independent variable with more than one dependent variables. Okay, that's still an ordinary differential equation. If you had more than one independent variables, then you get into partials. But as long as you only have one independent variable, no matter how many dependent variables you have, you're still in the ordinary thing, which is in the scope of this book. So you should be accustomed to seeing and working with other symbols to denote the variables. For example, we could denote the independent variable t, and the dependent variable could be x or x and y or whatever. Okay? So doesn't make a lot of sense why they're doing this here, except just to get you away from the xy mindset. Okay? So here's a function. X is equal to C1 cosine 4t. Here's another function. X is equal to C2 sine of 4t. Okay? Where C1 and C2 are arbitrary constants or parameters, and they're both solutions of this linear differential equation. Sorry. Now, I can't think what you call it. What order of derivative are you going to have if you have two independent variables? What order of derivative? That's the only way I can think of saying it. You think a first order differential equation is going to give you that? No, you only need one. So this is going to be second derivative. Got to have a second derivative. Okay? And since your dependent variable is x in both cases, this is going to be x double prime. And in this case, plus 16x is equal to 0. They're saying this is a solution, that both of those are solutions for this linear differential equation. Okay? Let's try it and see. What did we better do here? I wish I had left more room. I think I will erase this and make more room. Okay. Okay. What do you better do first? Take a derivative. Okay, x prime is equal to, and what's the first derivative of that first x? Anybody? Oh, that's Cal 1. We're through with that. I don't need to know that anymore. Okay, no, just kidding. Negative 4, C1, second, sine of 4t. Agree? Yeah, very good. Okay, now, want to go and do the first derivative of the second one, or take the second derivative of the first one? I don't care too much. Second derivative of the first one, okay? X double prime is negative 16 C1, second cosine of 4t, okay? Let's do the second x over here. I should probably do different color x's. Let's do that. What color you want the second x to be? Red, you said? Okay. Okay. So x prime of this one will be 4c2 cosine 4t. Is that what I heard? And x double prime of the second one is going to be negative 16 c2 sine of 4t. Okay? Now, let's plug the second one into this equation. That would be minus 16 c2 sine 4t plus 16 of that function, the red one up here, looks black but I underlined it in red, C2 sine 4t, and sure enough, that's equal to 0. Okay? But, also, let's go back to black. If you plug this one in, minus 16c1 cosine 4t plus 16, and the x up here is c1 cosine 4t. Sure enough, that's also equal to 0. So both of those are solutions for that second order ordinary differential equation. Okay? And of course, you have to have two. Now here's the part I don't know if they're going to mention now, but I'm going to mention it to you now. Anytime you have two independent solutions, the sum of those solutions is also a solution. So you could say C1 cosine 4t plus C2 sine 4t, and that's going to be your general solution for the second order. I think they're going to say that. Yeah, well, let's see, are they? Okay. Actually, they start off with that, don't they? No, they don't. Oh, but they do say it at the end. They say, or the two-parameter family x equals c1 cosine 4t plus c2 sine is also a solution. So anytime you have two that are both solutions, you can add them together, and they form your, and they don't give it the name, but the general solution. Okay. Now, all right. I think I'm going to need to draw a graph, so let me go to my graph page and erase this. Okay. Okay. Y is equal to cx to the fourth. And you can sort of tell if they don't put a subscript, it's a single value. You could say C1, but if you only have one, you can just put C. Okay? They say that is an explicit solution of this differential equation. xy prime minus 4y is equal to 0. Let's verify. What do we do? Take a derivative. Y prime is equal to 4c x to the third. Okay, let's plug that in. X times 4c x to the third minus 4 times y, which is c x to the fourth. Is that equal to 0? I think just a cursory glance will tell you it is. This will be 4c x fourth minus 4c x fourth. Yeah, that's equal to 0. Yeah, that works. Okay? Now, they're going to suggest to you, let's graph two of these functions. The first is going to be when c is equal to 1. That's pretty easy. Okay? When c is equal to 1, they do this one in light blue, so I'll do it in light blue. Okay? When c is equal to 1, that would be x to the fourth. When x is 0, y is 0. When x is 1, y is 1. When x is minus 1, y is 1. When x is 2, y is 16. Okay. Off scale really fast, right? So basically it's going up extraordinarily rapidly, meaning it comes down and flattens out here and then goes up extraordinarily rapidly. Okay? They did their next one in red, so let's choose red. And they did y is equal to minus x to the fourth. Okay? X is 0, y is 0, x is 1. It's minus 1. When x is minus 1, it's also minus 1. And when x is 2, negative 16 in both cases. Okay? So again, they go very negative very rapidly. So this comes up here and flattens out real distinctly and then goes down and goes down very fast. Now they expanded their scale a little bit, so perhaps a little better than mine, but not too much. Okay? Now, let's go back to the original. Okay? This is true, this solution is true from all real numbers, minus infinity to infinity. Okay? All real numbers x. Okay? Now, most of the time we think of piecewise functions, you don't want to mess with them, especially taking derivatives and things like this. But if you can put together a piecewise function from a family, then that can work as well. And if you'll see, and you want a different color for this one? Not red, blue, or green. Red, blue, or black. Second, purple. Okay. Royal color. Okay. So here we're going to say, here's another function. Y is equal to the piecewise function of minus x to the fourth anytime x is less than 0, and positive x to the fourth anytime x is greater than 0. And, you know, there may be a part of you that says, you need an equal sign somewhere in there, and yeah, maybe you do. Either one of these could be an equal, because guess what? When x is equal to 0, both of those are 0. So basically what you've got then is this leg of your minus function and that leg of your plus function. Okay? So here is a solution. Now, it could be even weirder. We just chose plus 1 and minus 1, but if you'd chosen the plus 3/4 and a minus pi, you know, they'll look a little differently because they're done, but they still meet in the middle. And then you could have a weird looking thing here to a different weird looking thing up there, but it's still going to work because the 0, 0 is constant. Okay? And all those. So, don't know really why they threw this in here, except, yeah, piecewise functions can work if you're very careful about selecting them. And actually, when they did their right half, they did it with an equal sign there. They didn't put it in their piecewise defined function, but they did in the graph. I just said either one of them. One of them needs to have the equal sign. All right. The next thing is systems of differential equations. Hey, wait, weren't they hard enough? Just a single one? Why do we need to go to a system? Okay? Up to this point, we have discussing single differential equations consisting of one unknown function. But often in theory, as well as in many applications, we must deal with systems of differential equations. A system of ordinary differential equation is two or more equations involving the derivative of two or more unknown functions of a single independent variable. There's the key. Ordinary, it has to be single independent. For example, if x and y denote dependent variables and t is your independent variable, then the system of equations, let's go back to this one. And again, this is sort of nebulous. You're not going to do a lot. In fact, you're not going to do anything with it now. But here would be how this looks. Let me go back to black. Okay. dx dt, first order okay, equal to some function. Now, what would be the variables that might be in that function? Certainly x and t, okay? But then you have another one, dy dt, and that could have a function g, and what would be the ones there? Y and t. But since this is a system of equations, this one could have a y in it, this one could have an x in it, okay? But it's a function only of those variables. Since they're connected together in a system, you could have y's or x's in each one of them, okay? Now, if you did have a system such as that, the solution of that is a pair of differential functions. One would be x as a function of, okay, let me write that again. I got the talking faster than I was writing. X is equal to some phi 1 of t, and y is equal to some phi 2 of t. Okay? On some common interval I. Both of these must be on the same interval I, satisfying each of the equations. So you can have the other variable in if it's a system of equations. It would be hard to have it if it wasn't. Okay, so, but if it is a system. Now, let me mention just briefly a little bit of what the I would be. Now, by the way, I is an interval of t. You're always your independent variable. Okay? If this phi 1 was from negative 15 to 2, but that's the only place it was good, and the phi 2 was from negative 3 to 45, then this common interval must be negative 3 to 2. Okay? You'd have to have everything inside that. Even if you some values you throw out here, some values you throw out there. Or if the first one was here and this was here, you use just this one. Okay? If they're disjoint, then it won't work. You can't do it. You can't have a system of equations. Okay. Now, first time I taught the course from this book, I tried to go through the remarks and see if we could make them make sense. And they seem to be just pulled from somewhere way far away, having almost nothing to do with what we've talked about. I'm not saying don't read it. Read it, but don't get bogged down in it. Because when I tried to teach from it, I'd say, okay, but why are they saying this? Why is this coming up now? A lot of this stuff we'll see again, but when you see it, they'll just find it. But you might want to take a look at it now to see. But I will mention one. Elementary and non-elementary functions. Okay? We will run into this before. Let me mention what the elementary functions are. Constant functions, y is equal to 17. Okay? Polynomial functions, you know what those look like. Rational functions, ratios of polynomials. Exponential functions, logarithmic functions. Trigonometric functions, and inverse trigonometric functions. Those are your elementary. Okay? That covers a lot, but it doesn't cover everything. Okay? Probably pretty much everything you've ever dealt with, but there are many other functions out there that are non-elementary. Okay? And that's not the same as transcendental, because E and log and some of those others are transcendental, so don't get those two confused. And then they do mention in their Roman numeral 6 the general solution, and I've already introduced that to you. Okay, homework exercises here. And the answers to selected odd number problems are in the back of the book. So if I assign any, and these are not required, but these are just things for you to practice on, if the answers aren't in the back of the book, don't sweat them. Okay? But most of the ones I'm going to assign, I think, will be. So you can do any of the odds 1 through 7. I think I assigned those before, maybe not. Do number 9. Do either 11 or 13 or both. Either 15 or 17. Do 19. Either 21 or 23 or both. Either 25 or 27 or both. Do 29. That's a piecewise defined function. Do either 31 or 33 or both. Do 35. Either 37 or 39. And 41. I'll guarantee you the discussion questions do not have answers in the back. I'm not saying don't do them. You can read through those, think through them, see how you would answer, but I don't believe they ever have the answers in the back. Okay? Now, I'll bring your attention to going to say problems 49 and 50, because those are problems. If 49 has an answer in the back, you can give it a shot. If it doesn't, don't sweat it. But I was thinking 50 was actually what I was going to say about 51. What I was going to say about 50 I thought was what's actually in 51. 51 mentions another function. It's called, it's a one-parameter family of functions called the folia of Descartes. Okay? Now, the only reason I'm mentioning that, Descartes' name is mentioned, there's a potential paper topic. Okay? You don't have to have a mention in the book, but that's what I'm trying to say is you'll find little places like this that you, if you can't think of anything you want to write on, you might run into this. Descartes would be good. What is the folia of Descartes? What does it do? What problem does it solve? Where did he get it? Where did it come from? Any one or more of those things could be a potential paper topic if it's something that interests you. If it isn't, you might find something that interests you more. But when you see something like that, you might want to investigate it as a potential paper topic. So that's the only reason I mentioned that. All right, let's move on to 1.2. Don't let me get too carried away because I have another class coming up right after this one. All right, let's go to 1.2, initial value problems. And I already snuck that concept into you when we're looking at families of solutions. To pick out one single solution, you need to know some particular value of that function. Okay? So we're often interested in problems in which we seek a solution to a differential equation so that that solution, y of x, satisfies certain prescribed side conditions. Okay? This is what you're going to run into in the real life. Okay? You know that this situation can be described as a differential equation. But you also know you need it to fit this particular problem. So at this point, this thing's going to be true. So that is your initial condition or a condition, okay? So in generic terms, let's say you had, and hopefully you didn't, a nth derivative of y with respect to x to the nth power, okay? You know this is some function. Can you tell me some of the things that could be functions of? X, say again, y, y prime, y double prime, dot, 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 up to the nth derivative of y. Perfect, okay? Now, that by itself is going to give you what? What's going to be the solution of that? The general solution. You're going to have a family of functions with how many parameters? n, the number of derivatives you have. So that's going to be an nth, would you say order? I can't remember how they express that. Nth order, nth degree family of solutions. So you have a C1, C2, C3, C4, up to Cn. Okay? Now, if you want a single solution, you're going to have to come up with conditions. And if you put this, that y of x0 is equal to y0, say, y prime of x0 is equal to y1, y double prime at x0 is equal to y2, dot, 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 and go all the way up to y, the n minus first derivative of y at the value x0 will then be y sub n minus 1. Okay? Yeah, and they don't do the parentheses around that. You have to do it around the derivative thing to let you know you're taking a derivative, not a power. Okay, where y0, y1, y2, y3 are arbitrary constants. Okay? Then, and here's where the term initial comes from. And in some senses, I don't really care for the term initial, except that's what everybody uses. At some fixed value of x. Okay? When I think initial, I think x equals 0. It doesn't have to be that, but some fixed value. So I'll kind of, my gut want to call it a fixed value problem, not an initial value problem. Because this isn't necessarily when x is equal to 0. To me, that's what, especially if you were dealing with t's. T equals 0, to me, that's the initial value. Okay? At time t equals 0. But fixed value. But you have to have your function and each of the derivatives, not the last one. Okay? If you have the last one, you have a trivial situation. You know, you have more constraints on it than you need. But you need to know what it is, the function y at x0, and then all the derivatives up to next to the last derivative. Not the last. You don't put the last derivative in there. Okay? But you'll need to know that. That then pinpoints it to one single function, y. Okay? Before that, you have a family of solutions y. Okay, does that kind of make sense? Okay, so this is called the nth order, okay, initial value problem. I'm going to write it one time. Initial value problem. Okay? From now on, I'm not going to write initial value problem. It's going to be an IVP. Okay? Initial value problem. Okay? When I was in grad school, I was a member of a Christian organization. It was called InterVarsity Christian Fellowship, and they had their own publishing thing, and it was InterVarsity Press. So when I think IVP, I think InterVarsity Press. But no, it's initial value problem. So same initials, but it means something else. Okay? So all these conditions here are called then your initial conditions. These are called the initial conditions. And I'll probably say initial conditions, but the book will quite often just call it the ICs, the initial conditions. Okay. So, when you're trying to solve an nth order differential equation like you have up there, okay, it frequently entails first finding an n parameter family of solutions. You'd have to find all that family of solutions in different ones, you know, with C1, C2, C3, up to Cn, okay, or whatever you wanted to name those. And then you start using the initial conditions to solve for each one of those C's. And it can be a pretty long process. Most of the time we won't have more than third order, I don't think, okay? So it won't be incredibly awful, but sometimes it can be pretty bad. But usually things get simpler as you go, okay? So let's look at a geometric interpretation of that. It's really hard to do since they don't give you a specific function. So I'm just going to hold the book up and show it to you. Or maybe I should write. I'll write down what they write and then I'll hold the book up. So let's clear this off the screen. What if you have this? dy dx is equal to f of xy. Okay? Now remember too, in the setup of this, I should have mentioned that before I erased it, you always went up to f of x, y, y1, y prime, y double prime. You go up to y to the n minus, the n minus first derivative of your dependent variable y. Okay? You never have that. On this side you have your n. On that side you only go up to n minus 1. And that's why you only have initial conditions to the n minus first derivative. Okay? So on this one, since it's the first derivative, we don't include the first derivative over here. It's just x and y. Those are the only two variables you can have in that. Okay? Now, this is your n equal 1 case, by the way. So how many initial conditions do you need here? 1. And that usually is designated as f of, let's see, that's not f, that's part of the problem, it's not part of the solution. y0 of x0, I'm sorry, getting things crossed up. Y of x0 is some y0, okay? Now, of course, y is a function of x. X is the input, y is the output, so that's going to be your answer. So this is going to be for some x0 out here, your y0 is going to be up there. And that's going to define it, okay? This is when n is equal to 1, first order differential equation, d2y dx squared, okay? And they're going to call this f as well. What would be your variables for f? X, y, and y prime, first derivative. So this is n equal 2, okay? So what conditions would you need? Y of x0, you can still call y0, but what other one do you need? Y prime at that same value, x0, that condition, whatever that condition was, and that usually you will call y1, okay? Your subscripts are just markers. They don't really tie to anything, but they're just markers. Again, if your function is the derivative of x, your first derivative is generally going to be a derivative of x. When you plug in the value for x, that x0, you're going to get some y value, and that'll be y1. Okay. So the subscripts can be a little squirrely sometimes, But just remember this. The x subscript is usually the 0. The y subscript talks about which derivative you're doing. The 0th derivative meaning just the function, the first derivative there. If you had higher order here, then you keep on going. And the subscript for the y corresponds to which derivative you're taking of y. I don't know if that's helpful or not. Now, with that in mind, let's look at what they could be. All right. For the first one up there, let's say that you have a family of solutions that are this: the green curve, the yellow curve, the blue curve, the red curve, and the beige curve, whatever that one is, okay? Now, if your point x0, y0, you know has to be on the curve, and that happens to be right there, then you know the blue curve is the function you use. And, you know, the blue curve, whatever your C was that gave that to you, because this is only going to have a single C in it. Okay, this one down here is going to have a C1 and a C2, okay? And if you know that x0, y0 is there on the curve, but that the derivative of y is going to be this y1, then the slope of that curve is going to be here. So you could have a lot of different functions going through the same points or other things, but this is the one that both has a initial value there at the point and a slope of this value there. So that gives you position and slope, and you know which one to choose. I didn't find this a particularly instructive illustration, but this is what we gave. Okay. Whoa, you let me do it, didn't you? Okay. We'll begin next time with example 1. And since we didn't do any examples in this section, we won't pick out any homework exercises here. So that does it.